Today we're going to take a little break from kinetics and talk about some of the basics of organic chemistry. Organic chemistry is basically the chemistry of carbon. Carbon has a huge diversity in the different ways that it's able to bond with other elements, and there are literally millions of organic compounds. So what we're going to do today is to look at some of the major classes of carbon-based compounds. Up first is a family of compounds known as the hydrocarbons. So a hydrocarbon is simply any compound that contains only carbon and hydrogen. And within the family of hydrocarbons, there are a few subdivisions. The simplest of those is the alkanes. Alkanes contain only carbon-carbon single bonds and carbon-hydrogen single bonds. Because of this, they're largely unreactive. They're really not very interesting. About the only thing they do is burn. Alkanes burn very well, but that's about all. So you'll know an alkane because its name will end in the suffix ane, A-N-E. One example of this is methane, CH4, which you've probably heard of before. If a compound contains anything at all that is more complicated than a carbon-carbon or carbon-hydrogen single bond, it's said to have at least one functional group. A functional group is just a small group of atoms or bonds that predicts how a compound is going to react. So, I said earlier there were literally millions of organic compounds. So as an organic chemist, if you had to learn the properties and reactivity of every molecule individually, that would be a pretty insurmountable task. But functional groups let us focus in on the important part of a molecule to know where a reaction is actually going to happen. And if you know what the functional group is, you can predict how that compound will react under given circumstances. So we're going to go through a list of several of the most common functional groups that you should be able to identify in a compound. First up is the alkene. Alkenes are just compounds that contain carbon-carbon double bonds, in addition to all of those single bonds. So because of the increased electron density within that double bond, there's two shared electron pairs instead of just one, that tends to make alkenes a little bit more reactive. They have names ending in ene, E-N-E, and one example is ethene, also known as ethylene, which is a plant hormone responsible for ripening. If we take it one step further to a triple bond, we get what is known as an alkyne, which have names ending in -ine, Y-N-E. One example is ethyne, also known as acetylene, which is the stuff in acetylene torches. These also tend to burn very well. The last of the compounds that can be purely hydrocarbons is the aromatic or phenyl group. This is a ring of 6 carbons with alternating single and double bonds around it. These tend to be incredibly stable, they have very unique reactivity, and it can be kind of hard to get them to undergo reactions, but if you have the right conditions, they will, and very few other things react the same way. So the simplest example of this is benzene, is just that 6 carbon ring without anything attached besides hydrogen. Now we're starting to incorporate some other elements, in this case oxygen. When you have a carbon connected to an OH group, it's known as an alcohol. Note that this OH is not OH-, it is not a hydroxide ion because this is not an ionic compound. So when OH is connected to a carbon, it's an alcohol. They have names ending in -al and are things like ethanol, which is the compound responsible for drunkenness when ingested. If we instead attach a halogen atom to a carbon, we get what's known as a haloalkane or haloalkane. X is generally used to represent any element from the halogen family, and any of the halogens can be incorporated in the same way. So in this case, they're named with a prefix, and the prefix will vary depending upon which halogen is present in the compound, either fluoro, chloro, bromo, or iodo. One example is dichloromethane, which is a really commonly used organic solvent because of its mild polarity. When we bring in a nitrogen, we get what's known as an amine. Amines are organic weak bases. Some of them can actually get pretty strong, not generally quite as strong as a hydroxide, but under the right conditions they can be pretty substantially basic. They also tend to smell really bad. They have names ending in amine, and one example is methylamine. So this next one, the carbon-oxygen double bond, is known as a carbonyl, and that in and of itself isn't really a functional group. It's more of a class of functional groups. So depending upon what's attached on either side of that carbonyl, on either side of that carbon-oxygen double bond, there are several different types of functional groups, but they all fall under the general blanket of carbonyl compounds. So when you're identifying functional groups in a compound, you should never just call something a carbonyl, because it's always part of some larger picture, and I think you'll see what I mean in the next couple slides. The first of the carbonyl compounds is known as a ketone. So you'll see we have that carbon-oxygen double bond in the center, and what makes it a ketone is having carbon atoms directly attached on both sides. So when you have a carbonyl with 2 carbons on either side, you call it a ketone. They have names ending in -one, example shown below. If instead of carbons on both sides, at least one side has a hydrogen atom directly attached to that carbonyl bond, we call it an aldehyde instead of a ketone. The chemistry of aldehydes and ketones is almost identical, except that aldehydes tend to react faster. There are a few reactions that only aldehydes can do, but for the most part the two are very similar. Ketones have names ending in -al, and one example is methanal, shown below. When that carbonyl group has an OH on one side, this is known as a carboxylic acid, and as the name suggests, they are in fact weak acids. Their names end in oic acid, and one example is ethanoic acid, which is also known as acetic acid, which I know you are familiar with, and is the primary component in household vinegar. In an ester, we still have that carbonyl group, and there is an oxygen on one side, but it is not an OH, it is an oxygen attached to another carbon. So these have names ending in -oate, O-A-T-E, such as methyl ethanoate. The methyl refers to what is referred over here, what is attached over here, rather, and the ethanoate part refers to the rest of the ester group. When we have a carbonyl bond with a nitrogen atom on at least one side, these are known as amides. These have names ending in amide, and one example is ethanamide. And that brings us to the end of the functional groups that you need to know. So these are certainly not all of the functional groups represented in organic compounds, but they are many of the most common and many of the most important in a lot of cases. So when you're looking at a large organic molecule, there may be several functional groups. This compound has 4, so pause the video here and see if you can identify them. So this compound contains a carboxylic acid, an amide, and 2 alcohol groups. So the knowledge of what functional groups are present in a compound would let us predict how it would react under certain conditions. So there was some additional practice with this posted along with the video, so give those a try, and the answer key was posted as well. Enjoy the rest of your snow day.